Adrian, please, the stage is yours.
Thank you very much, Alex, for the introduction and also for inviting me to speak. Let me make sure, can everyone hear me all right?
Yep.
Okay, so I'll start by sharing my screen. So let's see. Can you see my screen now?
Yeah.
All right, so yeah, so I'll tell you about some work I've done in the past year or so about stability and Sophic approximations for product groups. And property tau, as Alex mentioned, is in the title here because it's one of the main tools that I use in this work. So for roughly the first half of the talk, it'll be sort of more of an overview and a bit of motivation for what I did. So there'll be some overlap with some of the things you've seen so far. Hopefully, no one would be too bored. But if you want me to speed things up, just let me know. Or if there's any questions, stop me at any moment. So first, I want to tell you about Sophic approximations. So let me go ahead and review the notion of approximate homomorphisms. So as we've seen already, the setup is to consider typically countable groups gamma. And if you have a finite set X, you endow this group of permutations of X with the normalized Hamming metric, where the distance between two permutations sigma and tau is the number of points at which they're different divided by the cardinality of the set. So this is a metric which takes values between 0 and 1 being normalized. And then a sequence of maps from the group gamma to the symmetric groups of some finite sets Xn is an asymptotic homomorphism if the homomorphism relation is satisfied asymptotically, so the distance between sigma n of gh and sigma n g sigma n of h goes to 0. So you can think of this as being approximate homomorphisms, or if you think of a homomorphism to a symmetric group as being an action on a finite set, these are almost actions in a precise sense. All right, so perhaps before I define what a Sophic approximation is, let me give you some examples of asymptotic homomorphisms and how these arise. So, so let me take a sequence of homomorphisms to symmetric groups, but now symmetric groups Yn, of symmetric sets Yn that are possibly infinite. And you see why I'm taking them possibly infinite. So first, if all the Yns are finite, then obviously this is a sequence of homomorphisms. So in particular, it's a sequence of asymptotic homomorphisms. So for instance, what you can do is, and sort of this describes all such homomorphisms that are transitive, you can consider left multiplication actions of gamma on coset spaces gamma mod gamma n for some finite index subgroups of gamma. And this gives you homomorphisms from gamma to the symmetric group of the coset spaces. So now there's another construction of asymptotic homomorphisms that are not homomorphisms. And this, I think Oren already explained last time. So here's what you do. You start again with a sequence of homomorphisms, and you assume that all the Yns are finite. And now what you can do is take to some subsets of Yn that as n goes to infinity have roughly the same cardinality as Yn. So you're removing a smaller and smaller proportion of the points of Yn. So if you do that, then you can define an asymptotic homomorphism of gamma to the symmetric group of the smaller set by restricting sigma n. So just to remind you what the
sorry, it's xn over yn converges to 1?
1, yes. Yes, that is a type of, thank you. Yeah, so yeah, I want xn over yn to go to 1. So then you can define this asymptotic homomorphism by restricting. So the way you can do it is you can imagine, because xn contains most points in yn, most points on xn are mapped to xn through one of these permutations. And you just have to tweak the permutation on the set of points that are not that are not mapped back to Xn. So you can do this procedure of restricting so that you no longer have a homomorphism, but you have an asymptotic homomorphism or an almost action on a smaller subset. And I should mention that there is a more general procedure here to construct asymptotic homomorphisms. So now let me go back to assuming that Yn are typically infinite and take a sequence of subsets Xn of Yn, which are almost invariant, meaning that when you look at sigma n of G for some fixed G, this leaves Xn almost invariant as n goes to infinity, of course, relative to the size of Xn. If you have this condition, then it means that for every fixed G, G moves Xn almost on top of Xn. So again, you can define a new asymptotic homomorphism by restricting sigma n. Again, you have to restrict to the set of elements of Xn that are mapped to Xn and then change this on the complement. All right, and I'm mentioning this because this gives you a second or third construction of asymptotic homomorphisms. So if you take an amenable group, you can look at the left translation action of gamma on itself. So this is a homomorphism from gamma to the symmetric group of gamma. And because the group is amenable, this action has left invariant sets. These are the Fellner sets of the group. And if I take such a sequence of Fellner sets Xn, then I can apply this procedure to get an asymptotic homomorphism from gamma to the symmetric groups of the sets. All right, so these are some examples of how you can build asymptotic homomorphisms. So let me go ahead and talk a little bit about Sophic approximations. So what are Sophic approximations? These are specific kinds of asymptotic homomorphisms that are, well, they are almost free. So if I take an element G in gamma, which is not the identity, I want the Hamming distance between sigma n of G and the identity to go to 1. This means that the proportion of fixed points of sigma n of G goes to 0 as n goes to infinity. So sigma n of G, or G if you want, acts more and more freely on the set Xn. And then a group gamma is Sophic if it admits a Sophic approximation. So if it admits an asymptotic homomorphism with this additional freeness condition. So somehow being Sophic means that the group gamma has almost actions on finite sets that are also almost free as you grow the set, the cardinality of the sets. And let me say a few words about Sophic groups. So these are a very interesting class. So first, it's a very large class. It contains all amenable and all residually finite groups. And in fact, if you look at the list of asymptotic homomorphisms that I defined before, well, using those given by Fellner sets, you can construct a Sophic approximation of amenable groups. And then residually finite groups are also Sophic because you can look at left multiplication actions on coset spaces. So it's a large class. On the other hand, it's a very interesting class because being Sophic has important consequences. And I will mention here just one result, which is very easy to state, and is due to Louis Bowen, who showed, for instance, he showed a much more general result, but he showed that if gamma is a Sophic group, and you look at the Bernoulli shift action on the 2 full shift or the 3 full shift, so you look at 1, 2 with the uniform measure assigning 1/2 to each weight, or 1, 2, 3 with the uniform measure, and you take these spaces to the power gamma, then the resulting Bernoulli actions are not isomorphic. And I'm mentioning this because this is not known without the sophicity assumption. And so this brings me to the third remark, which is that it's still open to find examples of non-Sophic groups, but it's believed that such examples should exist. All right, so here's the sort of general problem that that is natural here and also motivates what I'm going to tell you later on. So if you're given a Sophic group gamma, you may wonder, well, what are all the Sophic approximations of gamma? Is there any way to describe them? Perhaps classifying them is a bit too much to ask, but you want to know, what can you say about a general Sophic approximation of gamma? So let me say one result which gives a good answer to this for amenable groups. So Alec and Jabo in 2011 showed that if you have an amenable group, then any Sophic approximation can be constructed by taking an essentially disjoint union of Fellner sets. So Fellner sets give you Sophic approximations, and somehow they have a result saying that any Sophic approximation comes from Fellner sets. So that's for amenable groups. And the second large class of Sophic groups that I mentioned is that of residually finite groups. And let me mention that, well, a group is residually finite. So one way you can see this is if and only if the group has a Sophic approximation, which each sigma n being a homomorphism. Okay, so in particular, if gamma is residually finite, we know that it has a Sophic approximation by homomorphisms. And if you want to classify the Sophic approximations of gamma, the best you could hope for is to say that the converse holds, and any Sophic approximation is by homomorphisms, essentially, or in other words, any Sophic approximation comes from finite index subgroups. So this brings me to this notion of stability that you've seen before. So group gamma is stable in permutations, and from now on I'll refer to it as P stable if any asymptotic homomorphism from gamma to symmetric groups of finite sets Xn is close to an actual homomorphism. So this means that there exist homomorphisms from gamma to symmetric of Xn such that the Hamming distance between sigma n of G and tau n of G goes to 0 for every group element as you let n run to infinity. Okay, so in a very precise sense, this says that any asymptotic homomorphism of gamma comes from homomorphism, is a perturbation of homomorphisms. All right, and if you've ever worked with ultra products, this will make sense to you. If not, well, let me just mention that there is a characterization of stability in terms of ultra products, and is really deciding whether a group is stable or not is a lifting problem. So a group gamma is P stable if any homomorphism from gamma to the, if you want, metric ultra product of finite symmetric groups lifts to a homomorphism to the product of the symmetric groups. All right, and let me also mention that there's a much more general framework here that Alex mentioned just before the talk. So you can define a notion of C stability not only with respect to permutations, but whenever you have a class of groups C, which are equipped with some bi-invariant metrics. And I'll just mention here some of those. So for instance, if you take the class C to be the class of all unitary groups, you have many choices of norms there. So you could use the operator norm or the Hilbert-Schmidt norm or the Frobenius norm, which is sort of the non-normalized Hilbert-Schmidt norm to get various notions of stability, matricial, Hilbert-Schmidt, Frobenius stability, all of which have been studied quite a bit in the last few years. And the last thing I want to mention regarding this general notion of stability is that when C is a group of matrices, well, stability, at least of Z square, is equivalent to a classical question. So if you're looking at stability of Z square, well, you're looking at almost asymptotic homomorphisms from Z square to groups of matrices. Well, to give an asymptotic homomorphism of Z square, you just have to check that the images of the two generators commute or almost commute. So this is equivalent to the classical problem of deciding whether two almost commuting matrices with respect to whatever norm you care about are near in the same norm commuting matrices. Okay, so this is a problem that goes back to the 60s or so. All right, so so this is the notion of stability in permutations. Again, a group is p-stable if any asymptotic homomorphism is a perturbation of a sequence of homomorphisms. And perhaps I'll go through a quick overview, and this is not complete, just a mention a few results about groups that are both p-stable and not p-stable. But perhaps before I do that, let me ask if there's any questions so far.
I remember, I forgot how it's proved. When I define this almost homomorphism as Sophic, I didn't require that the distance between non-zero element, non-trivial element will go to 1, but only that it's bounded away from 0. And I remember that there is a trick to that the two are equivalent, but now I cannot remember myself. What's the trick? Do you remember?
Yes. So the trick is if you have permutations that are away from the identity, you can do the product. So you, on the product space, xn times xn times xn, you can just inflate the space.
But you have to do it for each element separately, and then you take some kind of a diagonal or something.
That's right. The diagonal product will be farther and farther from the identity.
I see. So this is kind of this is the trick. Okay. Thank you.
Oh, thank you. All right. So so let me mention some examples of groups that are p-stable. So one obvious example is that of the free groups. Of course, there's no relations to check there. So if you have an asymptotic homomorphism, then you can build a homomorphism by just looking at the values on the generators. And that would be asymptotically close to your original asymptotic homomorphism. Glebsky and Rivera noticed more than 10 years ago that also finite groups are p-stable. And then Arjancheva and Păunescu proved that abelian groups, so in particular Z-square, are p-stable. And a couple of years ago, Becker, Lubowski, and Tom gave a general criterion for stability of amenable groups. So they proved that an amenable group is p-stable if and only if every invariant random subgroup is a limit of finite index invariant random subgroups. I will not spend more of time on this. Perhaps there'll be talks later in the series about this, but let me just mention that they were able to use this to prove that various amenable groups, including polycyclic groups and the Baumschlag solitar group BS of 1n, are p-stable. And the method that they introduced relating with IRSs was used also last year to give more examples of amenable groups that are p-stable. And I'll just mention a couple of results here. So my colleague Tianyi Zheng proved that the first Grigorchuk group is p-stable. And then Levitt and Lubowski proved that the Lamplighter group, Z mod 2, reproduct with Z, is also p-stable. And I'll end this slide with a result which is not per se about p-stability, but Lazarovich, Levitt, and Minsky proved that surface groups are flexibly p-stable. And so this is a notion that's very close to p-stability, and we don't know how far it is, in fact, from p-stability, but I will discuss later on. So I'll have to explain later on what flexibility means here. So let me go ahead now to tell you a bit about what's known about non-p-stable groups. Becker and Lubowski and Tom in the same paper were able to also use their criterion to provide some examples of amenable groups that are also residually finite but are not p-stable. And the result that we saw last time, due to Oren, Becker, and Alex, is that any residually finite group with property T or even property tau is not p-stable. And Oren already went through this argument, so maybe I'll just show you just a quick overview of their proof, because this leads to the notion of flexible stability that's critical to my talk. So how did they do this? Well, this is using the method of building asymptotic homomorphisms by restriction that I mentioned earlier. So if you have a residually finite group gamma, you have lots of homomorphisms to symmetric groups. And then by removing one point from the set 1 through Kn, you remove one of the points and you'll get an asymptotic homomorphism sigma n prime, which is still close to the original one. This is, you take your set 1 through Kn, remove one point, adjust your homomorphism to be an asymptotic homomorphism. But now, of course, if gamma is p-stable, this new asymptotic homomorphism, sigma m prime, on the set with Kn minus 1 points has to be close to an actual homomorphism tau n. And you see I have two relations of closeness here. Sigma n is close to sigma n prime, which is close to tau n. So this means that sigma n is close to tau n. But what is this? Sigma n is an action of your group on a set of Kn points. Tau n is an action of your group on the set of Kn minus 1 points, and they're close. Okay, close in this Hamming distance. Well, property T then gives you, well, of course, there's quite a bit of work involved here, but it gives you that also, if you assume some irreducibility conditions, the sigma n and tau n would have to be conjugate. I'm not going to tell you what that means, but that would force that the sets on which sigma n and tau n act would have to be the same, which is not the case here because one is 1 point less than the other. So this is the rough overview of what they did. But again, what I want to emphasize is that this uses the construction of asymptotic homomorphisms by passing to a smaller subset and restricting. And motivated by this, they introduce the notion of flexible stability. So group is flexibly p-stable if for any asymptotic homomorphism of the group, so to set symmetric groups of sets Xn, there are homomorphisms to larger sets Yn, such that the cardinality of Yn over that of Xn goes to 1. And so the set Yn is just slightly larger than Xn. And your asymptotic homomorphism sigma n is close to tau n. It's close to tau n after you restrict tau n to Xn. Okay, so flexible p-stability says that, well, it may not be the case that any asymptotic homomorphism is close to a homomorphism on your set, but this is true if you're willing to enlarge the set by adding a few more points that by adding a zero proportion of points asymptotic. Okay, so this is the notion of flexible p-stability. And let me mention that you can make this even more flexible if you want by removing this assumption that the cardinality of Yn over Xn goes to 1. So you could even not only require that Yn contains Xn and no other condition on Yn, and you might even take Yn to be infinite. Okay, the point is that this condition, the Hamming distance between sigma n of G and tau n of G restricted to Xn are close. Well, this automatically will force that Xn is an almost invariant subset of Yn under the permutations given by tau n. Okay, so this will come up a little bit later, but again, for flexible p-stability, this is the definition. And we mention here that, so Becker and Lubotsky's result shows that SLNZ is not p-stable. We don't know whether it is flexibly p-stable for n at least 3. And related to this, I should mention that if PSL5Z were known to be flexibly p-stable, then Bowen and Burton proved last year that they can construct a non-Sophic group.
Peter Burton will speak exactly about that next week in the seminar. So it's a good preview for his.
So you see, it's somehow proving that things are not flexibly stable or p-stable. It's kind of interesting in its own, but also proving that things are p-stable has quite amazing application. So so I guess that this is pretty much all I want to tell you in terms of examples. So now let me go ahead towards the main subject of my talk, which is stability for product groups. And so I'll start with a remark. If you take two groups, gamma and lambda, which are p-stable, then clearly their free product is p-stable. Because again, just like for free groups, it's very easy to define a homomorphism on a free product if you have homomorphisms on both of the factors. And then the question that motivated my work from last year is due to Oren and Alex and Andreas Tom. So they asked, if you have two p-stable groups, gamma and lambda, is their direct product p-stable? And you could see why this is somewhat of a natural question, because if gamma and lambda are p-stable, then and you have an asymptotic homomorphism of their product, then you know that when restricted to gamma, you can perturb this to a homomorphism, and when restricted to lambda, you can also perturb this to a homomorphism. So the question is whether you can do this at once and perturb both of them in such a way that the images commute. And I should mention that there's basically a variant, sort of a particular case of this question was asked a year before by Louis Bowen. And he asked whether specifically the free group on two generators times the integers and F2 times F2 are p-stable. Okay, and so the main result of some work I did last year is that this is both of these questions have negative answers, and this is a consequence of the following theorem. So assume that you were given two groups, gamma and lambda, and gamma admits the free group on two generators as a quotient, while lambda doesn't have property tau. Okay, so then under these assumptions, gamma times lambda is not flexibly p-stable. So in particular, it's not p-stable. So it's clear what having F2 as a quotient is. You can just think of gamma being F2, but there's many other groups. Sort of this is related to the concept of large groups that factor onto free groups. In particular, this forces gamma to be a non-amenable group. Okay, so let me just tell you what having property tau means. So this is Alex's notion, which for a group lambda requires that the unitary representation of lambda on the direct sum of all of these Hilbert spaces. So you look at little L2 of lambda mod delta, where delta is a finite index subgroup, and you remove the complex multiples of the scalars. So you require that all these unitary representations have spectral gap, or in other words, they don't have almost invariant vectors. Okay, so it's if you want an isolation for the property for the finite dimensional representations of lambda. And the fact that, so I won't go more into property tau, there's a lot known about property tau, but the only thing I want to mention here is that any group that admits an infinite residually finite amenable quotient, just think of the integers, doesn't have property tau, because this is the condition that I need. So in particular, in the theorem, you can just restrict to saying gamma factors onto F2 and lambda factors onto the integers, then gamma times lambda is not flexibly p-stable. So as a corollary, immediate corollary of the theorem, we get that if you take a direct product of two free groups, two nanobillion free groups, or the direct product of a nanobillion free group and z to the d, then these are not flexibly p-stable. So in particular, these two groups, F2 times Z and F2 times F2, are not flexibly p-stable, so they're not p-stable either. All right, so what I'm thinking to do next is tell you a little bit about how this theorem is proved, or rather the corollary. And to keep things simple, I will focus on one specific case, which already incorporates a lot of the ideas. So the case I'll focus on is the direct product of F3, the free group on 3 generators, times the integers. Okay, so this is covered by the corollary. You'll see right away why I need F3 and not F2. So the point is that F3 has F2 as a free factor. And so I should say that there is some flexibility built in this theorem and actually in its proof, which allowed me to prove that if the theorem holds for a group, then it holds for any larger group containing this group as a finite index. So you can see right away that if it holds for F3 times Z, it holds for F2 times Z, and so on. All right, so so this is another line of the proof for showing non-stability of F3 times Z. So I'm going to assume that gamma, my first group, is F3. This factors onto F2, and lambda is Z, which is prototypical group with Dow property tau. And I'm going to denote by sigma to be the free group on 2 generators, so that gamma is the free product of sigma with the integers. All right, so what is the goal? The goal is to prove that this direct product, F3 times Z, is not p-stable. Well, what does this mean? Well, it means that we need to construct an asymptotic homomorphism, which is not close to any homomorphism. Okay, so there's two parts here. One is to construct this asymptotic homomorphism sigma n, and then to show that it's not close to any homomorphism. It doesn't come from perturbing any homomorphism. All right, so to construct sigma n, let me start with the following fact. So there are finite groups xn with cardinality going to infinity, and you can take xn to be one of these finite SL2 groups, so SL2 of Z mod Kn, together with onto homomorphisms from sigma, which is the free group on 2 generators, and a homomorphism from lambda, which is the integers, such that the cardinality of the image of lambda goes to infinity. And moreover, the unitary representation of sigma on the L2 spaces of Xn. So these are the unitary representations that you get by, well, using the action of sigma on Xn has spectral gap. And here I'm perhaps the simplest way to use it is through Selberg's result, that this congruence about the property tau for congruent subgroups of SL2Z and even for free groups. Okay, so this is a known fact that I'll take as the starting point here. So how do we construct sigma n? So so again, I want to construct sigma n on gamma times lambda, and I'll first do it on sigma times lambda. So this is on F2 times the integers. And there you can just use the left-right homomorphism. So because Xn, so there's a homomorphisms from sigma and lambda to Xn, I can define sigma n of GH as being the left-right action of sigma times lambda on Xn. So on the left, I act by multiplying with Pn of G, and on the right, I multiply by Qn of H inverse. Okay, so that's how you construct it on sigma times lambda. So now I want to extend this to gamma times lambda. And to do this, I only need to define sigma n to the extra generator that I have in the picture. So I have to define it at T and the identity, where T is a generator of the integers. Because again, gamma is sigma free product with the integers. So this is the missing piece. In order to check that sigma n is an asymptotic homomorphism, I will need sigma n of T and the identity to asymptotically commute with lambda. Okay, because in the free product of F3 with the integers, this is the only relation that you need to check asymptotically, that everything in F3 asymptotically commutes with everything in the integers. Okay, so this is where the lack of property tau for lambda comes into play. And perhaps I'll go over this quickly, but lambda doesn't have property tau. Here, lambda is the integer, so it's very specific. So as a consequence, you can find subsets of Xn that are almost invariant under the right action of lambda on Xn. And moreover, you can have such sets with prescribed cardinality, more or less, prescribed relative cardinality. So I want the cardinality of An over X, that of Xn, to be between 1/7 and 1/6. And moreover, I can do this in such a way that I can find an element of Xn which takes my set An disjointly from it by acting on left multiplication. Okay, so then how do we define sigma n of t and identity? Well, so you should really think of t, which is part of gamma, as acting on the left. So sigma n of t and identity acts as multiplication by gn on An, multiplication by gn inverse on gn times An, and identity otherwise. But what you should bear in mind here is that in each part of the definition, I'm using left multiplication with an element of Xn. This will asymptotically commute with right multiplication by lambda n because, of course, left multiplication always commutes with right multiplication, plus An is a set that's invariant by right multiplication with lambda.
So you are using all the time now that the set Xn is also a group, right? That's why you can talk about Gn times An.
That's correct. Yes, yes, yes. So the group structure is very important. Yeah.
So you take something, but should understand what does it mean if Gn is in Xn and it's true for every element, how can you arrange a Gn An intersection An is empty for every or for some?
For some Gn, yes.
Oh, yes. I see. You pick up it. So now I don't understand. You choose Gn. What is the Gn here?
Gn is just some element. I just need one element in the. Can you not see the? It's just some element in Xn.
I see. You choose an element in Xn in the group such that this specific group, which is almost invariant under the H and from the right, is completely not invariant, so kind of under the action from the left. Okay, yeah, that should be possible, I guess. Yeah.
Yeah, because you can imagine if you have a set A in the group, then you can compute what's the average of the intersection of GA with A. And the average would be smaller than the cardinality of A. So then you can remove that intersection and then you get disjoint of A with GA.
Okay. So now you define the sigma n. So okay, you need to define only for one more element, and this is your definition now.
That's right. Yeah, this is it for the definition. You need to check that it's like I was saying, because An is right almost invariant under lambda, and the definition of sigma n at this element involves only left multiplication. Sigma n of t and identity will asymptotically commute with the right action of lambda. Perhaps simplest is to think of An being actually invariant under the action of lambda. If this were the case, then I've split the space into three pieces: An, Gn, An, and the rest. And on each one, T acts by left multiplication, which obviously commutes with the action of lambda, right multiplication.
Yeah.
Okay. So this is the construction, and perhaps I'll go over so how do we prove that these are not close to homomorphism? So this is a part of a sort of general result, and this is really where the core of the proof lies. So I call this it's a rigidity result for asymptotic homomorphisms. So here's what this says. So take an asymptotic homomorphism. So think of the one we just constructed, sigma n, such that the restriction to sigma times lambda is the left-right homomorphism Pn times Qn. Okay, so you remember sigma n was constructed exactly like this. And then assume that for such an asymptotic homomorphism, I have some homomorphisms tau n such that the distance between tau n and sigma n goes to 0 pointwise in the Hamming distance. All right, so then I can find a different homomorphism tau n prime, which still has the same property, that tau n prime, the distance between tau n prime and sigma n goes to 0, but this has the additional property that tau n prime is also the left-right homomorphism when restricted to sigma times lambda. Okay, so if sigma n is close to an actual homomorphism, then I can take that homomorphism to agree with sigma n on the smaller subgroup sigma times lambda. And you can see that this is quite a restriction, because obviously now I can assume that tau n is prescribed on this large subgroup of my group, so sigma times lambda. So I won't say anything about the proof other than it uses the spectral gap of the representation. So property tau for the congruent subgroups of the free group is critical here. And let me just point out why this implies the sigma n, that the sigma n's we constructed are not close to homomorphisms. Well, if gamma times lambda were p-stable, then the asymptotic homomorphism constructed in part 1 would have to satisfy the hypothesis of this theorem. It would be close to some homomorphisms tau n. But then I've claimed that this implies the following condition. It implies not only that sigma n of t, the generator of the integers, asymptotically commutes with any element of lambda, but it does so in a uniform fashion. So if you look at the distance between sigma n of t, sigma n of h, and the reverse sigma n of h, sigma n of t, this goes to 0 uniformly over all elements of lambda. And why is that? Well, so this is because, let's see, so on, so how does this go? On lambda, sigma n is equal to tau n prime, right? Because this is how tau n prime is given. On t and identity, sigma n is close to tau n prime of t and identity. Okay, so on the two elements here that appear t and identity and an arbitrary element of lambda, I have that this is close to tau n prime of t and identity, tau n of prime of e and h, and the same on the right. And you can check that this sort of because tau n prime is a homomorphism, and t and h commute, well, tau n prime of t and tau n prime of h will commute as well. So this is really a one-line consequence of the property that tau n prime has. I don't know if this was clear. So does anyone have any questions about?
Yeah, actually, I don't see it. Can you just say it in words? Like what's the point here? If so you assume this asymptotic homomorphism is close to homomorphism, then it's close to such an homomorphism whose restriction to the F2 cross Z is the original homomorphism, the left right.
Right.
Okay, why this bring to a contradiction now?
So the way you can, so consequence of this is that if you look at sigma n on the generator of the integers, this is
What is sigma? What is sigma n? The original. I mean, after corrected. You mean?
Well, sigma n is the original one. Tau n prime is the correct
Ah,
one.
okay, okay. Which is anyway, they are both agree to each other on F2 cross Z.
That's right. So they agree there. So if you look at this formula here, when I write sigma n restricted to lambda, this is the same as tau n prime restricted to lambda.
Right.
But then sigma n restricted to the generator of the integers on the left side is close to tau n prime restricted to that generator.
Yeah.
So on the right side, I have equality. On the left side, I just have approximation, but at one element.
Mm-hmm.
And tau n prime is a homomorphism. So the well, its values at the generator of the integers and lambda commute.
Mm-hmm.
So the same. So this will give you the uniformity on the estimate, because the point is that you on the infinite set that you have here on lambda, you actually have equality.
Okay, so now why this is a contradiction?
Yes, this is not something that I can explain, but this comes from a little calculation, because you can see now, this is, let me just say this is a very strong condition, right? Because it it says that sigma n at the generator of the integers uniformly commutes with this group of permutations, the sigma n of lambda.
Mm-hmm.
So then you can, still requires a long argument, but one of the things you can prove, I mean, you can explicitly say what sigma n at t must be. If it's if it asymptotically commutes with something, it has to be close to something that actually commutes.
Okay, so where is the now here you use again the spectral gap, or it's not anymore?
So the spectral gap is just used to prove the theorem.
Uh-huh.
And I haven't told you anything about the proof of that, but the spectral gap comes into the proof of this theorem. After that, you no longer need spectral gap. So really it's
okay.
The fact the spectral gap is used here is really illustrated by this estimate, because what spectral gap typically buys you, and it does in this proof, is that you have a pointwise estimate, pointwise invariance that is translated into uniform one. So I have this almost commutation pointwise, and somehow you can use spectral gap to get it uniformly.
Mm-hmm. I mean, I try to see if I can just see it without writing formulas, saying that assume you have an homomorphism of the group of the B group, like of F3 cross Z, which agree with the original right-left homomorphism on F2 mod Z. Now, because this element must commute with the action from the right by Z, then if there's kind of a primitivity, if you divide the action of, if something commute with it, then it must be more or less a power of it, and that's not the case here, because you started with something which keeps this A, right? I mean, somehow.
Yeah, you are right that you can do this once you get this condition, it becomes very explicit.
Very easy. Okay, so I think
you get a contradiction sort of very hands-on.
Mm-hmm. Okay.
Because you see sigma n of t and identity is very specific, in fact.
Yeah.
Especially for the integers, you can write down a formula. All right, so okay, so this was the outline of the proof for F3 times Z. So so let's see, Alex, how how much longer do I have?
No, you have. We go slowly, and we have more than we usually, including all question and everything. We go for 75 minutes, not for 60.
I see. Oh, very good. So yeah, so let me tell you a little bit more about them. I guess maybe I should go back. Yeah, for a second at least. A strengthening of these theorems for certain groups, and then tell you just a little bit about some more recent work from this summer. So again, this theorem says that if you factor onto F2, gamma factors onto F2, and let's say lambda factors onto the integers, then gamma times lambda is not flexibly p-stable. Let me now go ahead and show you what the strengthening of that is. Okay, so let gamma be one of the groups that were treated in the corollary. So it's either free group times free group or free group times ZD. This is the D. And here's a result which strengthens the failure of flexible p stability for gamma. So gamma, what I could prove is that gamma admits in fact a Sophic approximation such that there are no homomorphisms tau n on a larger set yn with no restrictions on yn, and then again here yn can be infinite, such that sigma n of g is close, asymptotically close to the restriction of tau n of g to xn. Okay, so this clearly strengthens the lack of flexible p stability, and it does so in two ways. So first, in that earlier theorem, I only need to provide an asymptotic homomorphism with this with a certain property, not a Sophic approximation. So we can have a Sophic approximation, and moreover, I don't need the set yn to be just xn plus a small portion of points. It can be an arbitrary set containing xn.
So in particular, you said yn can be infinite here?
It can be infinite, yes.
Okay.
But again, what you should keep in mind is that this condition here, what does it mean? So by it, I really mean that you measure, so this is the normalized Hamming distance on xn. And you can define the Hamming distance on xn for any two functions whose domain is xn, right? Because you can just count the number of points at which they're different and divide by the cardinality of xn. So that's what this means. So in particular, this does constrain, does put some constraints on xn. So it implies
that sometimes we call it very flexible stability. So we're really proving that it's not only that it's not flexible, stable, it's not even very flexible, stable.
Yeah,
I'm not sure that it's just a good name to call it very flexible, stable, because the meaning, what we meant when we call it was very flexible, stable. But when you say it very flexible, stable, people think that this is a stronger property than flexible, stable, because it's very flexible, stable.
That's right. Yeah, I don't think there's a good.
It's weaker than flexible. So you are, but it's interesting because you are proving here that it's not even very flexible, stable. Okay.
Yeah. So right. So that's yeah. So this is why it's the strengthening.
I see that Brad Henry suggested my English is not good enough. What does it mean? Flimsily stable.
Flimsy stable. Okay.
What does it mean?
very weakly, right? Sort of.
Very weakly. Flimsily stable. Okay, maybe good idea.
All right, and okay. So in particular, what this tells you for F2 times F2, which is what I'll focus on from now on, is that F2 times F2 admits a Sophic approximation, which doesn't come from a sequence of homomorphisms. So this is imprecise, but in particular, you can find a Sophic approximation of F2 times F2 such that there aren't homomorphisms to the same symmetric groups. which are asymptotically close to the Sophic approximation. And so what this says, this comes back to the question, to the problem that I sort of stated that towards the beginning of my talk, of trying to classify Sophic approximations of a given Sophic group gamma. So what this says in particular is that for F2 times F2, this ideal classification where you can say that all Sophic approximations come from homomorphisms or from finite quotients does not hold. So there's a more general potential classification that Louis Bowen put forward a few years ago, and this is in the last part of the talk, I'll tell you about that. So this involves a certain notion of a branch cover of an asymptotic homomorphism. I'm not entirely sure. I mean, I discussed with him, but I still don't think I fully understand what his motivation was. But I think it's more from it comes from graph theory and looking at the graphs associated with like the Cayley graphs, or I guess the Shire graphs coming from Sophic approximations. So if you have two asymptotic homomorphisms of the same group gamma, so sigma n from gamma to symmetric groups of xn, and then tau n from gamma to symmetric group of yn, you say the sigma n is a branch cover of tau n if, so you think of xn as being the set above, so there's a onto map from xn to yn, which you require to be onto, but also dn to 1. So the preimage of every point in yn has the same cardinality dn. And moreover, you require this map to be gamma equivariant, in the sense that if you apply sigma n upstairs and then you project down with tau n, you get the same as applying tau n composed with theta n. Okay, so for me, this is a notion of a factor map, if you want, between two asymptotic homomorphisms, and it's a fairly natural notion from this point of view. All right,
can I ask a small question?
Of course.
Since we're talking of asymptotic homomorphisms, is it interesting also to ask theta n only to be equivariant asymptotically, or dn to 1 asymptotically?
That is absolutely right, and in fact, in the results I'll present, that's how it goes. So if you, yeah, so that's natural. I don't think I'll have to look in my paper because I clarified exactly the the relationship where you allow this. I think so. My recollection is that if you allow yourself some flexibility, so you can go from this asymptotic equivariance to actual equivariance. This is not very hard to see because you can modify maps, by changing them a little bit in the Hamming distance, so that from an almost equivariance you get actual equivariance. So that's not really a problem. And the same with dn to 1. If you're asymptotically dn to 1, you can also modify the map. Again,
I see.
Thank you. Oh, you are welcome. So hopefully the statement that I'll give in a few minutes will clarify that more. So what was one of the reasons Louis was interested in this? So he noticed that if tau n, so the asymptotic homomorphism on the lower space, if you want, is a Sophic approximation, then so is sigma n. So if you know the sigma n factors onto tau n, and tau n is a Sophic approximation, the larger asymptotic homomorphism is also a Sophic approximation. So somehow this branch cover construction gives you a way of constructing new Sophic approximations from old ones. So you have this, any larger one is also a Sophic approximation. Okay, and the question he asked is whether every Sophic approximation of F2 times F2 is essentially a branch cover of a Sophic approximation by homomorphisms. So if I give you a Sophic approximation of F2, let's say sigma n, is it true that it has a factor which is a Sophic approximation by homomorphism? So where each tau n is a homomorphism. So here's the theorem that I proved this summer, which answers this question. So so there is a Sophic approximation of gamma, which is F2 times F2. So this is on sets Xn for which there are no homomorphisms from gamma to symmetric groups Yn and maps from Xn to Yn for finite sets Yn with the following two conditions. So the first one is that the maps are asymptotically equivariant. Okay, and the second one, this may seem a little strange, but is a freeness type condition as well. So I won't insist on this, the second condition, but perhaps I will just say that the second condition holds if you know additionally that tau n is a Sophic approximation and theta n is dn to 1, or even asymptotically dn to 1 will do it. Okay, so in particular, you can have a Sophic, you find the Sophic approximation of gamma for which there are no homomorphisms, which doesn't admit. So in particular, you get a Sophic approximation which doesn't admit a factor, which is a Sophic approximation by homomorphisms. Because if tau n were a factor, then of course this equivariance holds precisely. So this is 0, and the second condition holds as well, as I just mentioned. So so this is the consequence that I mentioned. So sigma n is not essentially a branch cover of a Sophic approximation by homomorphism. So this is the answer to Luis's question is negative. And what is the idea of the proof? So the idea is to construct sigma n in such a way that if you have any maps from Xn to Yn which satisfy conditions 1 and 2, and again the important condition is condition 1, which says that the map is asymptotically equivariant, then any such map must be asymptotically 1 to 1. So rather than dn to 1, it has to be asymptotically 1 to 1. So you cannot have so it's really not a true branch cover. It's just a cover. It's really an injection. Or if it's also on 2, it will have to be essentially a bijection. So having this, if you have this, then it means if your map is asymptotically 1 to 1, again, by tweaking the sets a little bit, it means that I can think of Xn as being a subset of Yn, because I have a 1 to 1 map from Xn to Yn. But then if you look back at this sort of strengthening theorem that I presented on the previous slide, that precisely constructs Sophic approximation sigma n with this property, that you cannot enlarge the set to find homomorphisms whose restrictions are close to your original. So the whole idea here is to construct some Sophic approximations on some sets Xn such that whenever you have almost equivariant maps to some homomorphisms, this forces the map to be 1 to 1. Okay, so there's no index, if you want, for the map going on. So again, I don't want to get into the full details of the construction of sigma n, but I'll end the talk with a slide in which I'll tell you a little bit about what's used in the proof, because I think that's more interesting than the proof itself in a way. So you already saw that I used property tau in the previous construction of sigma n. So here I need a refinement of that, and I need specifically this work of Alex with Alon and Wittgerson from 2001, where they proved that this expansion is not a group property. So I'll tell you specifically what I need from their construction. Oh yeah, so perhaps before that, the result I mentioned before applies to F2 times F2, and now I'm going to switch again to some larger free groups, F3, F5 times F3. This is again like the first approximation of the proof. Then you can go to specific free groups you want. So what did Alon, Lubowski, and Wittgerson prove? So they proved in particular that you can find some finite groups Xn together with an onto homomorphism from F4, so the free group on 4 generators, and from the free group on 3 generators with the following, I guess, 3 properties. So I want F4 to have property tau with respect to these quotients, xn. I want F3 to not have property tau with respect to the quotients. So this already gives me a sequence of finite groups xn such that with respect to 4 generators, they have property tau, but with respect to 3 other generators, they don't. And moreover, I want the intersection of the kernels of these QNs to be trivial. Okay. So in particular, this I think I might need a bit more than just that, but the point is that I would want the QNs to really give me a Sophic approximation of the free group on 3 generators. I don't want to generate things where I factor F3 through some smaller group and then map it to Xn. All right, so so I should mention here that I don't know whether in this construction you can take Xn to be a simple group so that you have all of these. Okay, so the construction of Sophic approximation or almost homomorphism that I gave you earlier, you can plug it in here to construct a Sophic approximation of F5 times F3 in such a way that when you restrict it to F4 times F3 is the left-right homomorphism Pn times Qn. Okay, so this is the sort of machine that I described earlier. And now, so now let's assume that there are some homomorphisms from F5 times F3 on some set Yn, which is a factor of the sigma n. So I have some almost equivariant maps theta n from Xn to Yn, which verify the assumption of the field. Okay, so again, you start with the sequence of finite groups Xn. These come equipped with homomorphisms Pn, Qn from F3 and F4, and with them you can use my previous work to build the Sophic approximation of F5 times F3, which when restricted to F4 times F3 is the left-right homomorphism. And now I'm assuming that sigma n factors onto a Sophic approximation by homomorphisms. So the observation is here that if you have such a factor map, of course, when you look at Yn, the partition of Yn given by partitioning in the sets with one element, this is a partition that's almost gamma invariant, right? It's obviously because gamma acts by permutations. When you lift this up to Xn, you get the partition of Xn into the pre-images of points in Yn. And because of the almost equivariance of theta n, this will be asymptotically gamma invariant. I'm not defining what this means, but you can imagine what it means for a partition of a set to be almost invariant under an action. Well, you simply, if your partition is x1, x2, xk, you require that, so this will be almost invariant under a permutation of the set alpha, if when you look at alpha x1, alpha x2, alpha xk, well, you have a matching of these sets such that the total symmetric difference is very small to the relative to the dimension of the set. All right, so these are asymptotically gamma invariant, and using property tau, you can prove that any asymptotically gamma invariant partition has to come from a quotient group of Xn. Okay, so we can actually assume that Yn is the quotient of Xn mod some normal subgroup Zn. And okay, this is very, very vague, but you do some more work to show the Zn must be the trivial subgroup. Okay, and you can see here, so if Xn were a simple group, then Zn is either Xn or the trivial subgroup.
Why do you say that there is an open problem with a simple group? Nowadays, we know that there are simple groups which are expander and unexpander.
Yeah, but I need this additional condition with the kernels. I need the QNs to give me a Sophic approximation. So if you're thinking of Martin Casabo's work, then that won't be enough here because right, for the symmetric groups, you have generators which don't give you expanders, but those are, well, asymptotically, these give you a representation of a amenable group. Is this group with, I forget exactly, but I don't think those will give you a Sophic approximation.
I see, but maybe I have some construction for SLN, which is different based on Ramanujan complexes, and maybe there one can do. Okay, I have to think about that. Oh, now Martin is here, and he writes in the chat that he can modify his construction to have this property.
I see, very nice.
Okay.
Okay, so so theta n is asymptotically 1-to-1, and that's it really, because sorry, I don't seem to. Yes. Oh, I think that, yeah, I don't think I have anything else, because yeah, so theta n is asymptotically 1-to-1, and this is where I wanted to get, because then you can, this tells you that yn is a subset, sorry, xn is a subset of yn, and you can get a contradiction from what we discussed before. There you go. So I'll stop here, but of course, any questions, I'll be happy to.
Yeah. Let me ask you a question, then of course I'm sure there are some more. Is it possible that Bowen interest, because he wants to define a factor, something which would be similar to Fürstenberg, you know, as a factors of a dynamical system, and then there is this famous notion of Fürstenberg about disjointness of a dynamical system. Maybe one can define this notion of disjointness of Sophic approximation if they don't have a common factor, and maybe one can develop all this theory for Sophic approximation.
Well, I should say that so I discussed with him, I guess, a year ago over email, trying to clarify this notion. This factor is, I call them factor. I don't think he refers to them as factors. He just calls them branch covers. I think his motivation, forget, at that time, so he wrote this appears in some Oberwolfach proceedings from 2011, and I think he even mentioned that that time he thought that for surface groups, all Sophic approximations would come from branch covers. And this was maybe the intuition he had. He was wondering if this is also true from other groups of this kind, like F2 times F2. But at least I haven't heard him say anything about.
But anyway, I mean, it might be an interesting notion to develop anyway, because you see, if you take homomorphism, for two homomorphism, you can sort of define what does it mean for two homomorphism from a group gamma to say G1 and G2 to be disjoint if the image to the direct product is onto. You see,
right.
like, and then maybe one can make such a notion for Sophic approximation to be disjoint if they don't have a common factor, and develop such a theory. I don't see application right now, but it might be interesting. Anyway, okay, I don't want to talk too much, but rather maybe some other people want to ask questions. So please just don't wait for me to see you, but just please talk.
I have another also basic question about these branched covers. I couldn't understand, like maybe in the statement of this theorem you just proved. Yes, I couldn't understand exactly. You think of Xn as surjecting onto Yn, like this factor map should be I don't know, asymptotically onto in particular, right?
So that's the case in the definition of branch covers. In this theorem, I no longer assume that. I don't assume it's on too. So this is more, there's a bit more flexibility in the theorem.
I see, because this is why you needed your previous construction of xn only contained in yn, right?
That's right. That's right. Yeah.
I see. Thank you.
But you do like you need this construction, this condition too, which yeah, holds if
Okay.
theta n is d n to 1.
Okay, cool.
Okay. Somebody else wanted to ask? There was a
So
little
I might
noise.
have,
Yeah.
I might have it a little bit quick of saying that like you can modify my construction to get like that the kernels are essentially disjoint. Can you really send me an email with like exactly what you need so that I can think about it?
Sure, sounds good. Yeah. I will. I think what I said here is pretty precise, except that yeah, I want QNs to be a Sophic approximation. Yeah,
So
but
you
I'll follow up with you.
So you just want expanders and Sophic approximations for symmetric group, nothing else.
So no. So
No, the other way around. The non-expanders should be Sophic approximation.
yes. So the expanders, I want those to be a Sophic approximations too, but that's not essential. The non-expander part, the ones lacking spectral gap should be a Sophic approximation.
Can you do a quick translation for someone like me that doesn't come from this field? So if how do you translate the property tau, not property tau, to expansion, not expansion, using this homomorphism?
So for a group, right, if you have a group or a sequence of groups xn, and let's say that you fix a set of generators on each one of a fixed cardinality, then you can define expansion by just requiring that the Cayley graphs are expanders. So so here, if you look, for instance, at Pn, which is a homomorphism from F4 to Xn,
yes,
requiring that F4 has property tau with respect to these quotients, is the same as requiring that when you look at Xn, with the generators coming by projecting the 4 generators, those are form a sequence of expander graphs.
Okay, so in this case, expansion goes with the property tau.
That's right. It's equivalent in this context. Is the same as property tau.
So here the statement expansion is not a group property. Is saying that you can choose different generators. You can get the same sequence of graphs or some, like using the same sequence of groups. You get different graphs. These are expanders. These are not expanders. So it's not something that's originate from some property of the groups.
That's right. That's right. Yeah. So expansion doesn't depend just on the group, saying that if you have 10 generators in your group, you necessarily get an expander. Yeah.
And how does the intersection relate to Sophic?
Well, this I realize now that so if you assume, moreover, that these kernels are nested. So let me just say this. Maybe we can. So if you have a sequence of maps from a group to finite groups, and well, the finite groups are let's say quotients, right? Then to get a Sophic approximation, you just need a sequence of finite index subgroups, a chain of finite index subgroups of your large group whose intersection is trivial. Let's say that they're finite index and normal, and their intersection is trivial. So that would give you a Sophic approximation.
Okay.
Because this left actions on coset space become more and more free.
Thank you.
You're welcome.
Okay, thank you very much, Adrian, for excellent talk.
Okay, can I still ask a question? Just
Oh, there is more questions? Sorry.
yeah, just I mean, it's a bit of a technical issue, but so I read the paper for the first proof that you presented, and I thought about this, whether these sets Yn can be infinite or not. So, and for this very flexible stability. And as far as I understand it, I mean, this result is still true if the second factor is amenable, but I don't think it's true. So I'm not sure, I don't have a counterexample, but I don't see that you can copy the proof for let's say f2 times f2.
Which result are you mentioning?
Yeah, the first one. So just this.
This one?
Yes, this one. Yeah, but it's a very technical thing, I guess. So it might not be interesting for the rest of the audience. I mean, so the thing is, you're using this lemma, and you have this set xn, which is nested in this big set yn, and what you're then doing is kind of, you look at xn as almost invariant. So you're looking at the possible images that xn can have, and then you kind of average over them. So possible images under the corrected homomorphism, and you're looking at the action of the second factor. And I think you need to do this averaging, and you can only really do this if the second factor is amenable.
I'm not. Maybe we can talk over email or something, because I don't.
Yeah.
I'm not really sure what you mean by averaging here.
Yeah, it's completely fine. Yeah, I was thinking whether to write an email or ask now, but
no,
yeah, okay.
Yeah. I just don't know. I remember my proof roughly well, but I don't know exactly what you mean by averaging.
I wanted to ask another small question.
Yeah.
So, yeah, I don't want to keep too many people here, but the curiosity kills me. Like, are some of the groups which you showed here not to be p-stable? For example, the direct product of two free groups. Do you think they have potential to be not Hilbert-Schmidt stable?
Yes. So there, yeah, that's a good question. So Hilbert-Schmidt stability at first looks pretty similar, but it's actually, yeah. So I should mention that it's known, and it's fairly easy to see that if you look at the free group on two generators times the integers, that is Hilbert-Schmidt stable. But I believe that f2 times f2 is not. But the methods here don't apply to that. I've tried in the past. So this method is not.
Which method would apply?
So I'm saying that the methods in this proof won't give you that f2 times f2 is not Hilbert-Schmidt stable, because well, the same method proves that f2 times z is not p stable, and that we know to be Hilbert-Schmidt stable.
But there is a proof by different method. That will be interesting. Okay, I hope that next semester we'll get to that at some point. Tatiana Schulman will talk about H. Hilbert-Schmidt stability, so we will hear more about that, even in this semester, and next semester maybe we can expand.
I'm sorry, but just to be clear, it's still not known whether f2 times f2 is Hilbert-Schmidt stable, or it's already known. Okay, good. Thank you.
What did you say, Adrian? It's known or not known?
It's not known. Yeah.
We say it's not known. I see. Okay, I don't want to keep people, especially those the local who wants to go to lunch. So we'll stop here. Thank you very much, Adrian. Give regards to Alireza and to Yefim and all my friends there. If you see them, or maybe you don't see them.
Well, over Zoom and committees, we see each other. Yeah. So yeah, thank you so much for the invitation, and thanks.
Thank you. It was excellent.